Compression pressure. Fluid compression occurs when an external force is applied to a fluid by its container. For example, the air inside a tire, a balloon, or an air tank is kept at a higher than normal pressure by its container. The walls of an inflated balloon, for example, try to contract and pull the air inside into the smallest volume possible. If you have ever blown up a balloon and then released it, you might have noticed that the balloon expelled the air already in the balloon. In other words, the balloon was trying to contract the air into the smallest volume possible until it was equal to the natural volume of the balloon. The force that you exert upon the air as you blow it up is transmitted equally to all surfaces inside the balloon. Depth pressure. Another cause of increased pressure in a fluid is gravitational pressure. The fluid's weight causes it to exert more pressure at greater depths. The greater pressure at the bottom of a swimming pool is caused by the pull of gravity, as is the pressure of the air around us. The increase in pressure at the bottom of an 8 ft deep swimming pool is about 3.5 psi because of the water weight overhead. At the bottom of the deepest part of the ocean, the pressure is greater than. Figure 7.22 hydrometer. 8 tons psi. Although it varies with depth, the gravitational pressure exerted by a fluid at a given depth is applied equally in every direction. As an exercise, let's put into practice some of this theory. Calculate the pressure, psi, of the water at the bottom of a tank that is 10 feet square and 20 feet deep. First, remember your formula for determining pressure, which is pressure equals force divided by area, or P equals F/A. Now, what are the values for force and area? Work from the premise that the weight of fresh water is 62.4 pounds per foot 3, and volume is calculated by length times width times depth. Force, F, equals weight, W, times volume, V. F equals 62.4 pound/foot 3, 10 times 10 times 20 feet. F equals 62.4, 2000. F equals 124,800 feet 2. And area, A, equals length, L, times width, W. A equals 10, 10. A equals 100 feet 2. Now back to our original formula of P equals F/A, where P equals 124,800/100 feet 2. Because you normally see pressure stated as pounds per square inch, multiply 100 feet 2 by 144, or the area of a square foot stated in square inches. P equals 124,800/14,400. P equals 8.66 pounds psi. Gravitational pressure is determined not only by depth, but also by the density of the fluid. Denser fluids exert more pressure at a given depth, because they are heavier and more forcefully attracted by gravity. Sea water, which is slightly denser than fresh water, exerts about 3% more pressure than fresh water at all depths. Mercury, the densest liquid, exerts more pressure at a depth of 3 feet than water does at 30 feet. Gravitational pressure depends on depth and the density of the liquid, while pressure caused by an external force spreads equally through the fluid, regardless of density or location within the container. Pressure in Pascal's law. When a fluid at rest is pressed upon, either from an external force or from the force of its own weight, it moves around and adjusts itself until the force, or pressure, at any point is exactly the same in all directions. Blaise Pascal first asserted this principle with this statement: the pressure applied to any surface of a confined fluid is transmitted equally in every direction throughout the fluid. So when you add air to a tire, the pressure you add at the valve stem is spread equally throughout the whole tire. Pressure caused by the squeezing of a fluid by its container acts equally in all direction, and is transmitted equally to all surfaces. Pressure and Boyle's law. When you lower the pressure on a gas, the volume of that gas increases. According to Boyle's law, if the temperature of a gas remains constant, its volume and pressure are inversely related. We can express that principle with this equation. P1/P2 equals V2/V1. For example, when 100.3 of a gas under 20 psi of pressure is compressed to a volume of 5.3, what will be the new pressure if the temperature remains unchanged? First, look at how the volume changes. By dividing 100 in 0.3 by 5 inches. 3, we see that the volume decreased by a factor of 20, 100 inches. 3 divided by 5 in 0.3 equals 2. According to Boyle's law, if the volume decreases by a factor of 20, the pressure must also increase by a factor of 20. Therefore, you can find the new pressure by multiplying the current pressure 20 psi by 20 to get 400 psi. In addition to Boyle's assertions, Charles's law states, if the pressure of a gas is constant, its volume and temperature are directly related. If either temperature or volume changes, the other must also change in the same direction and to the same extent. You can restate this with this equation. V1/T1 equals V2/T2. To simplify, if you heat a gas under constant pressure, its volume will increase. But if you heat the gas in a container of constant volume so that the gas cannot expand, then its pressure must increase instead. If the volume of a gas is constant, its pressure and temperature are directly related. P1/T1 equals P2/T2. Archimedes and fluid displacement. Have you ever noticed how objects seem to lose weight when you immerse them in water? Buoyancy is the tendency for an object to float when it is placed in a fluid. Believe it or not, all objects have buoyancy even if they sink. Because of their own pressure, fluids exert a buoyant force on the objects within them. This force is due to the difference in fluid pressures at different depths, and is exactly equal to the weight of the fluid displaced. Archimedes first discovered this principle, and asserted that the weight lost by an object immersed in a fluid is equal to the weight of the fluid displaced. Therefore, an object will float if it is lighter than an equal volume of water, and an object will sink if it is heavier than an equal volume of water. A 75-pound piece of wood, if forcibly submerged, might displace 100 pounds of water. The buoyant force would then be greater than the weight of the wood, causing the wood to rise out of the water, until it displaces only 75 pounds of water, and the forces are balanced. Have you ever wondered how a ship made of steel, which is much heavier than water, can float? A steel ship is not a solid piece of metal, but is more like a hollow steel box filled with air. Therefore, it is much less dense than an equal volume of water. A ship in water sinks to a level where the buoyant force pushing upward, the weight of the water displaced, just equals the total gravitational force downward, the weight of the ship and its cargo. At that point of equal balance between the two opposite forces, the ship floats. After the cargo is unloaded, the ship will rise as its weight decreases. When it is loaded again, it will sink until the weight of the water it displaces is again equal to its own weight. Submarines can float on top of the water, or maneuver under it by changing their buoyancy. A submarine on the surface floats by displacing a volume of water equal to its weight. To submerge, the submarine opens doors that allow water to flood into ballast tanks, compartments in the submarine. The tanks are flooded until the submarine becomes heavier and sinks to the point where it weighs exactly as much as the volume of water it displaces. At the point where the submarine is completely underwater, but not sinking further, it has neutral buoyancy. The submarine can then use its engines and rudders to maneuver to any desired depth, according to its ability to withstand the pressure of the water around it. To resurface, the submarine must reduce its weight by releasing compressed air into the ballast tanks to force the water out of the tanks and make the submarine lighter.